Hello, welcome back to part 2. One other thing I should have mentioned about part B of this question. You may remember a slightly different way of getting these pole values. It's useful in situations like this, and that is if you work out what the resonant frequency and the Q factor actually are, which is not such a bad idea, going from the equations we had, which were that 1 plus j omega over omega naught q plus j omega squared over omega naught squared. That is a general form of writing what we evaluated from the circuit to be 1 plus j omega rc plus j omega squared times lc. And therefore 1 over omega squared is lc, just equating the terms in j omega squared, and that means that omega naught is the square root of 1 over lc, and if we put in the values for that down here, 1 over the square root of lc gives me 1 mega radian per second, which in terms of hertz would be, just divide by 2 pi, about 159 kilohertz. That's accurate enough. Q, equating the coefficients of j omega here, we can see that 1 over omega naught times q is just CR, and therefore Q equals 1 over CR omega naught. Put the numbers into that. 1 over C times R times omega naught 0.045. Right, there is an approximate way to get the frequencies of the poles in the case where Q is a small number. And this is a small value of Q, so the approximate way would work perfectly well. And the approximate way is very easy to remember. The frequency of the poles, one of them is omega naught times Q, and the other one is omega naught divided by Q. So in that case here, that means that in terms of hertz, the pole frequencies would be 159 kilohertz times 0.04545 and 159 kilohertz divided by 0.04545, and that works out to be about 7.2 kilohertz for one of the poles, and the other one about 3.5 megahertz, which is exactly the same results as we got before. This is an approximation though. It's very important to remember that this is an approximate result, which is only valid for low values of Q below about 0.1 or so. If the value of Q is bigger than 0.1, or you don't know what the value of Q is, much better off to stick with the quadratic way of doing it, which always works. Anyway, let's move on to part C of the question. Using the graph paper provided, approximate frequency response of the network as a Bode plot. Okay, you can get 2 of these 5 marks by just knowing what a Bode plot is. Drawing it out with the axes labelled, gain, units of dB, frequency, units of hertz, and I'm going to use a logarithmic scale here, since that makes them easier to draw. Say 10 hertz there, 100 hertz here, 1 kilohertz, 10 kilohertz, 100 kilohertz, 1 meg, and 10 meg. And just by drawing out axes, with scales labelled with units will get you 2 of the 5 marks. Now, what about the actual shape of the frequency response of this network? Well, a bandpass filter at the resonant frequency, and you may remember that at the resonant frequency the complex impedance of the inductor and the capacitor cancel each other out. In other words, it looks like the impedance between this point in the circuit here and this point in the circuit here is 0. V out, therefore, is equal to V in. And if V out is equal to V in, then that means that the gain will be 1, which is 0 dB. So at the resonant frequency, the gain is 0 dB. That's always true for these second-order bandpass filters like this. Where is the resonant frequency? Well, we've just calculated it before. We found out that it was at about 160 kilohertz. So that's going to be around about here. 0 dB. Now, that is the maximum output that you can possibly get out of this potential divider. There's no way of getting V out bigger than V in from a potential divider like this, because both of the reactive components are on the same side up here. We know that there is a 0 at 0 hertz, so we know that we're going to be starting off going up at 20 dBs per decade. There is a pole at 7.2 kilohertz, so that would be around about here somewhere. And there's another pole at around 3.5 megahertz, so that would be around here somewhere. And the Bode plot would therefore look something like this. You would come up at 20 dBs per decade until you hit this pole, and then you would level off. And we know that we're leveling off to 0 dB, so we would draw something like this. Go along to the pole frequency and then head down at 20 dBs per decade. Now I've got this scale a little bit wrong because I can see that if that is there, that is there. If I'm moving at 20 dBs per decade, these two should be 20 dBs apart, and they're only about 10, so I think that would be a much more accurate scale. On the frequencies greater than the resonant frequency, I would carry on to the pole frequency here and then head down at 20 dBs per decade. And that's fine, that's it. You would come up at 20 dBs per decade to the first pole frequency, which reduces the gradient by a factor of 20 dBs per decade, so it's now going horizontally, until you get to the next pole, where the gradient bends down at another 20 dBs per decade. That's what poles do, and we're now heading down like that. That would be it. That would be fine. It does say, hence estimate the 3 dB bandwidth of the network. Well, the 3 dB bandwidth would be between this pole here and this pole here. That would be a good approximation of that, and that is 3.5 megahertz minus about 7.2 kilohertz, which is, well, to a reasonably good approximation, it's just 3.5 megahertz. The 7.2 is insignificant compared to the 3.5 mega. We can quickly check that. It's always a good idea to check that the results that you're getting are sensible, and you might have remembered the formula that the 3 dB bandwidth of a bandpass filter like this is the resonant frequency divided by the Q factor. Here, our resonant frequency is 160 kilohertz or so. We calculated that before. The Q factor, 0.04545. That is equal to, well, we've actually already done that sum here. That's this one, around 3.5 megahertz. So even if you had worked out the poles using the quadratic formula rather than the approximate way that I've described here, this would just confirm to you that you were on the right lines. that the 3 dB bandwidth is indeed the resonant frequency divided by the Q factor. Right, 5 marks for that. Moving on. Step responses. This is quite a common final part of questions on frequency responses. What is the step response? And 3 important things to know about step responses. Firstly, the initial value theorem. The initial value theorem states that if you set omega to infinity, then the magnitude of the frequency response is the step response output just after the step has arrived. So, if omega is set to infinity, h of j omega becomes, well, if j omega is very, very large indeed, then this term here is much, much bigger than this term, and much, much bigger than this term, so we can neglect these 2 terms in comparison with this term, since this term in omega squared will be much, much bigger than either of those 2. That would just give us j omega rc over j omega squared lc. That gives us the c's cancel out, the j omega at the top cancels out with one of those, that gives us r over j omega L. But if omega is heading off to infinity, then this is going to become 0. It's something finite divided by something absolutely enormous. That's going to tend towards 0. So, initial value of our step response, I'll call it V 0 plus, just after the step hits, will be 0. Second important thing to know about step responses, the final value theorem. Final value theorem states that if you set the angular frequency, the j omega, to 0, then the frequency response here will become equal to the final value of the step response. Here we've got h of j omega, when omega is 0, would become, well, this term on the numerator would just become 0. The 1 is still a 1. But this is a 0 because omega is 0, and this is 0 because omega equals 0. So we would just get 0 over 1, which is again 0. So we have a step response which starts at 0 and ends up at 0 as well. Third important thing to know about step responses is that the time constants of the exponential rises and falls are the inverses of the pole frequencies in radians per second. And we've got 2 pole frequencies in this system, and in radians per second they were 21.96 megaradians per second and 45 kiloradians per second. Right, when the step hits, both of these responses are going to be kicked off. They're going to start. If I plot the step response on a time diagram like this, always label the axes with units, then anything that happens that fast is going to be over before anything that happens this slowly has even got started. What's happening in this case is that we're going to start at 0, we're going to end at 0. One of these poles is going to make the output shoot up, the other one is going to make the output come down again, but it goes up much, much faster than it comes down. To plot this on a sensible scale like this, it's really going to be the case, if I put t equals 0 there, that the output is going to go up, and up so fast that you won't see it, because it's going up with this time constant, and then it will come down with this time constant, and that will just give you a standard exponential decrease all the way down. So I could write as a pretty good approximation that the output is V out e to the power of minus t over the time constant related to this 45 kiloradians per second pole. That's just 1 over 45 kiloradians 2.22 times 10 to the minus 5. And I can approximate the step response of this network as this form, just by looking at the low frequency pole. And when you've got two poles that are separated so much in frequency, it's a good approximation to say, well, anything that happens that fast will be over so soon you'll never see it. I will only consider the effects of this pole here. Start at 0, head up to about 1, and then all the way down like that. And that would do 5 marks. But you'll get a fair few of those marks just by applying the initial value theorem, the final value theorem, and noting that the time constants are the inverses of the pole frequencies in radians per second. If you can't figure out what actually that means, you would still get the majority of marks for this part of the section. Right, I think there's only a small little bit left in this problem, just the final part. And if you just look back at what your expressions for resonant frequency and Q factor are in terms of the components in the network, you will note that the resonant frequency is the frequency at which the inductance and the capacitance cancel out. It has nothing to do with the resistance at all, and therefore if you change the value of the resistor, the resonant frequency does not change. However, the Q factor is inversely proportional to the resistance, so if you decrease the resistance by a factor of 100, you would increase the Q factor by 100. The formula that we got for that was Q equals 1 over omega naught RC. So decrease R and Q goes up. Suggest a use for a network with a high Q factor? Well, a high Q factor, if we had a bandpass filter with a high Q factor, its frequency response would look something like this. Not very well drawn, it's supposed to be symmetrical. Gain dB, frequency hertz. You would get something like this, which is a filter with a very narrow bandpass region. In other words, it isolates a certain very narrow band of frequencies. Anything below those frequencies is attenuated, anything above those frequencies is attenuated. Classic application of this type of circuit would be a radio receiver where you're trying to isolate just one radio station to listen to. But just about anything sensible got the mark there. Okay, hope all that made sense. Next video, well, if you've got anything that you'd like me to talk about in particular, do let me know.